Hi everyone, my name is Irieid, I'm a developer and here I talk about machine learning. And today I'm going to show you how to build a machine learning model using logistic regression algorithm. Let's do this. Okay, so first we import our libraries. Torch is the main PyTorch library for deep learning. TorchNN provides neural network building blocks like layers, loss functions, activation functions. TorchOptim provides optimizers like Adam Optimizer, for example, one of the most popular, and we're going to use it today. Pandas for working with tabular data like CSV files, data frames. NumPy for numerical computations and array manipulations. Standard scaler, which scales numeric features to have mean 0 and variance 1, and we're gonna come back to this a bit later and I will explain this if you're not familiar. Train test split from scikit-learn library, which splits data into training and test sets. And these are metrics for evaluating classification performance. So it's ROC, AOC score, and confusion matrix. Also, I'm going to explain it a bit later. So first of all, we load our data set. I already have it here, and you will find the link in description where you can download it to try it by yourself. And then we need to assign meaningful columns names. What does it mean? Basically we have just numbers here. So if we go here to this doc, this is actually our German data doc for credit scoring. We can see here all the attributes, which are like number attributes, and we can see the names of these attributes. So you can find all the information here, and we just assigned it to the columns, so it's gonna be like easier to understand and work with data set. Then also, if we will go to this doc, we will see that we have a target here, and target here's values are 1 for good and 2 for bad. And so what we need to do is convert it to binary representation. So we map in 0, 1, 1, 0, 1 to 0, so good to 0, and 2 to 1, so bad to 1. It's just a standard for binary classification. Then we define categorical and numeric columns. Also, if you go to this doc, you can find that here we have some numeric values and categoricals, columns. Yes, so you can also have all this information here. So here we define it because we need to apply different preprocessing to each type, like to categorical and to numeric type. And this for ensure that numeric columns are numeric, because I had some problems with this exact data set, so I added this line. And then we convert categorical features into dummy variables. This is named as one-hot encoding for categorical columns. And now each category becomes a new column with 1 if the row has that category or 0 otherwise. So as soon as ML models require numeric input, this step is essential. So we have to convert categorical features to variables. Then we separate features and target. As you can see, this line means all columns except target are input features, and this line means that target column labels. So we get the values of target column. Okay, so here we split data set into train and test data. We can see that we're gonna have 20% of test set, and stratify equals y means that we keep the same proportion of classes in both sets, in training and test set. Random state is 42. It can be any number you want, so it just ensures reproducibility. Okay, so now we need to standardize numeric features. That's why we were separating it from categorical features. We use scalar, standard scalar, and what it does, It's just standardized numeric features with mean 0 and standard deviation 1. What is that? So mean is the average value of the feature, and variance measures how spread out the values are around the mean. And actually, standard scalar uses mean and variance to transform this data, and it gets mean and standard deviation. Standard deviation is the square root of variance. After scaling, mean of features becomes 0 and standard deviation becomes 1. So ML models perform better when features are on the same scale. And also, if we have some feature with huge values, it prevents this feature from dominating this model. So here we convert Panda data frame to NumPy arrays because it required for PyTorch. And this S-type ensures that this is compatible float type for PyTorch tensors, because then we convert to PyTorch tensors. Why we do this? First of all, PyTorch models require tensors as input. And also training and loss computation only works on tensors, like not on NumPy arrays. And this line on squeeze just actually adds an extra dimension, because neural networks expect targets in 2D shape, so we just need this one more dimension in this shape. Then we finally defined our logistic regression model. We used class logistic regression model and module, and this is a standard custom PyTorch model for logistic regression. We add a single layer, it's gonna output a score, and this line, torch sigmoid, converts score to probability between 0 and 1. Then we initialize model, loss, and optimizer. Model is gonna be our logistic regression model with X-train shape. 1 means the number of input features. Then we add weights. It's actually optional, but I was playing with these hyperparameters a bit, so I think that for this exact data, you need to use this and these exact numbers, because I was playing with this a lot. So it just balances classes. And here is our loss function. It's going to be binary cross entropy function. It's actually one of the most popular for binary classification. And we also use Adam optimizer with learning rate 001. Actually, we usually start with this learning rate, so it's the best value to start with. And Adam optimizer also one of the most popular optimizers. Then we go to our training loop. We're gonna have 500 epochs. Epoch is just like an iteration on our data. And we're gonna reset gradients here, optimizer 0 grad. Why do we need this? Because PyTorch saves like previous gradients, and if we don't reset gradients, we're gonna compute our loss like not right. And that's why we need first to reset like previous gradients to has the result of this exact epoch. Then we do a forward pass on training data. Then we compute our loss function. Then we do a backpropagation. And then we do an optimizer step, as just we update weights. Here we just print our results for every epoch, every 100 epoch. Then we evaluate our model. Torch no grad disable gradient computation. It's like we don't need gradients here anymore because it's not training, it's evaluation, and it's gonna be faster and saves memory. So Y probability predict probabilities on the test set, and then Here we have our threshold of 0, 3. Also, I was playing with this a lot to get the best result. And threshold of 0, 3 is lower than 0, 5, so it's more sensitive to positive class. So here it's just convert probability, see if it's more than 0, 3, then it's 1, so it's good, and else if 0, it's bad. I mean, in terms of our credit score. And then here we have our metrics. ROC score measures model's ability to distinguish classes. And if we got like 0, 5 result, it's more like a random choice. 1 is perfect, less than 0 and 5 is means that our model works very, very bad. And confusion matrix shows true positives, false positives, true negatives, false negatives, like model results. So it shows exact counts of predictions versus actual labels. So let's see how our model works. We see ROC here 0.8, almost 0.8. So it's not bad. It's more than 0.5. It's not 1, but it's not bad for this data. And we have our confusion matrix. So this 12 and 33 in the perfect world, it should be like 0, 0. But also we got the best result we could get from this data set. You can also try and play with hyperparameters, change something, and maybe you will get better results here. So I hope it was helpful. If you want more tech content, please subscribe to this channel, and all the links you can find in the description.